Okay, this is a solution to number 17 from energy, which looks like this. Um, this incline that's at 30 degrees and a spring and a cart. The cart has a mass of 1 kilogram. The spring has a constant of 250 newtons per meter. Yeah. Okay. And we're trying to figure out first uh, how much is the spring stretched um, when it's hanging at rest. And then second, um, come up with a function. So what's the speed of the object as a function of position? Okay, well, if you draw a free body diagram of this, here's what loads are acting. You have a normal force. You have a spring force that's either going this way or the opposite way. Call it F spring. And you have a weight force. This is non-conservative, but that's okay because it doesn't do any work. So we can still use conservation of mechanical energy. This one's conservative and this one's conservative. All right, so we know we're going to have to deal with the potential energy functions for the spring and for the weight. The potential energy for the weight is mgh, and the potential energy for the spring is 1/2 kx squared, where x is how far the thing is removed from the spring's resting length. And what we would like to do is get these expressed using a single variable. Once we do that, we'll be like well on the way to getting this. But right now, like, because we want to calculate these things given like where the cart is along that path. We just want a single number. Is it at positive 6 centimeters or negative 12 centimeters from some resting thing? We don't want the h and the x. Okay, so let's fix that problem first. So if we think of the spring's resting length is here, okay, I'm going to call, so this is, I'm going to call that 0x, and positive x is going to be like this, okay? Well, if this is 30 degrees, then how does the height relate to that x? If we call height equals 0 when x is equal to 0, we'll say that's also h equals 0. Then you can think of the height as negative x times the sine of 30 so negative x over 2. Okay. So now we have a way to represent the potential energy, all the potential energy, using a single variable. So this is equal to 1/2 kx squared minus, I'll write it as, it's mgh, but h is x over 2, so this is like negative 1/2 mgx. Okay, so that's the potential energy for this thing. And that's what we're going to use through this whole problem. For part A, we want to find where the thing has no acceleration. It's hanging at rest. And no acceleration means no force. So let's think of the x component of the force being equal to 0. Okay, I'm going to use, so what I have, I've already shown the direction of my x-axis, and I'm going to call this my y-axis. How do you get from the potential energy to the force? The x component of the force is negative partial derivative of the potential energy with respect to x. And so that is negative kx plus 1/2 mg, and that has to be equal to 0. And so it's at equilibrium when x is equal to mg over 2k. I guess we have numbers for this, and if you plug in the numbers, so mass is 1, g is 9.81, k is 250, you get about 2 centimeters. So that spring is stretched 2 centimeters. Okay, and now the second part is we want to come up with a function for the speed in terms of x. We can use conservation of mechanical energy. The total potential energy at instant 1. So instant 1 is going to be when it's released after being stretched 5 centimeters. So the potential energy is equal to, we have this expression here, so it's going to be 1/2 k times 0.05 squared minus 0.05 mg over 2. And if you plug in all the values for that, you get a number. And the number is 0.06725. This is energy, so, and everything's SI units, so that's joules. It's being released from rest, so the kinetic energy is 0. At instant 2, so now we're at some arbitrary length x. So the potential energy is, if you plug in all those values, you get 125 x squared minus 4.905 x. And we're trying to figure out the speed, so the kinetic energy, and I'm sort of going back and forth with notation, but let's call the potential energy U, the kinetic energy T. So the kinetic energy here is 1/2 times 1 times the speed squared. And now conservation of mechanical energy says 0.06725 plus 0 is equal to 125 x squared minus 4.905 plus 1/2 v squared. Solve for v, and you get square root of the quantity, 0.1345 minus 250 x squared plus 9.81 x. This is all in square roots. And so now you can enter in the length of the spring compared to its resting length, and this will tell you what the speed is at that instant. So if you put in 0 for x, you'll get the speed when the spring is at its resting length. So as the object moves through that resting position, that's the fastest it'll ever be going. And I guess the answer in that case would be square root of 0.1345. Okay, so yes, that is a very hard problem, but that's how to do it.